of today's lecture is going to be an introduction to the last kind of reaction that we have to talk about in this chapter, and that is the oxidation-reduction reaction, otherwise known as a redox reaction. All right, so as we had mentioned before, this type of reaction is going to involve the transfer of electrons from one reactant to another. So one reactant will lose electrons while the other reactant will gain those electrons. So we have an electron transfer between reactants occurring here. Now, just a couple definitions that we have to be aware of. The first is oxidation. So oxidation refers to the loss of electrons. So the species that loses or gives up the electrons, we say is oxidized. Likewise, we have reduction. Reduction means the gain of electrons. So the species that actually accepts the electrons or gains them is the reduced species. All right? So what I want to do is look at a really simple example of a redox reaction, and this is one that you've seen in lab and also one that we have talked about before in class. So this one is the reaction that occurs between solid magnesium metal and oxygen. And you guys know from prior experience, when this reaction occurs, we end up making the grayish colored solid magnesium oxide. So I think in the lab you do this in a crucible, so you know what the magnesium starts out as. That's a shiny metal, and you end up making the chalky grayish magnesium oxide. All right, so this is an example of a redox reaction. This one, unlike many redox reactions that we talk about, you can actually balance by inspection. We're going to find out a little bit later that we have a specific method for balancing redox reactions. But this particular one we can do by inspection. Now, what we want to do is show that this is actually an example of an oxidation-reduction reaction, in the sense that one species is going to give up electrons and the other species is going to take those electrons. So let's focus on our two reactants here. Our first reactant is magnesium metal. Since it's not magnesium ion, but rather elemental magnesium, it carries a charge of 0. It's neutral. Likewise, that's going to react with oxygen gas. Since that's molecular oxygen, we also know that that also will have no charge. It will be neutral. Now, when those two things react with each other, we're going to make a salt, magnesium oxide. Now, the salt itself is neutral. But if I were to divide the salt up into its component ions, you guys know that we're going to have magnesium ion, which carries a 2+ charge, and oxide ion, which has a 2- charge. So what I'm going to do is I'm going to show how the electrons got transferred from one species to another to prove that this is indeed a redox reaction. So what I'm going to do here is I'm going to tie the magnesium on the left to the magnesium on the right. And if we do that, we'll notice that each magnesium here starts out with a 0 charge, but each magnesium on the right ends up with a 2+ charge. In other words, I'm converting magnesium element to magnesium ion. Now if you notice, if I go from a neutral to a 2+, I've lost 2 electrons, right? That's how I get there. So since the magnesium lost the 2 electrons, we say that the magnesium got oxidized. Okay? So I can put that down here. Now, let's take a look at the oxygen here. Now, again, oxygen started out as neutral, and it went to the oxide ion. So we see here that the oxygen actually gained electrons as it moved from 0 to a 2- charge. Now, since the oxygen gained electrons, we say that the oxygen got reduced, right? Because reduction is the gain of electrons here. All right? So, there's one other thing that we can talk about here, and we'll just sort of summarize what we said right up here. Magnesium on the left-hand side in its elemental form got oxidized. It lost electrons. Now, we call it the reducing agent. So as a general rule, the thing that gets oxidized becomes the reducing agent because it allows for the reduction of the other species. In other words, if the other species, the oxygen in this case, gains electrons, those electrons have to come from somewhere. They come from the magnesium. So that's why we call the magnesium the reducing agent. Alternatively, we have oxygen here on the left, we saw over here in our balanced reaction equation that the oxygen gained electrons to go from elemental oxygen to oxide ion. It was reduced. It gained electrons. Because it got reduced, we call it the oxidizing agent because it facilitated the oxidation of the other species, right? So as the oxygen gained the electrons, it had to take them from the magnesium, hence oxidizing the magnesium. So we call the oxygen, in this case, the oxidizing agent. It's the species that gets reduced. Now another way that we're going to typically look at this, and I'm going to be a little bit loosey-goosey about it here in the sense that I'm not going to necessarily try to balance anything here, is we can separate our overall reaction into what we call half reactions, where one reaction represents the oxidation and the other half reaction represents the reduction process. So from the magnesium side, again, just sort of summarizing what we said before, I can write a half reaction here just in terms of the magnesium. Now, again, for my other reaction on the left over here, we saw that magnesium lost 2 electrons to become magnesium ion. So we're going to put those electrons in there as either reactants or products. Now, since the magnesium gave up the electrons, I'm going to put them in here as products. All right, so we saw in this case, per magnesium atom that I've got, it's going to lose 2 electrons to make magnesium 2+, and there are the 2 electrons we lost. All right, so that's an oxidation half reaction. In other words, the magnesium is giving up the electrons. Now, of course, once we give those electrons up, they have to go somewhere. So that means we also have to have a reduction half reaction. I kind of sort of balanced this one out just so that it would all make sense based on what I had here on the left. So what we saw here is that O2, that's a molecule of oxygen, gave up some electrons so that I could make 2 oxide ions over here. So if I wanted to just mass balance this as I did here, what we're going to notice here is that I go from a neutral charge all the way to a 2 times 2, which is a 4- charge. So I had to actually pick up 4 electrons to make that happen. So in this particular case, the electrons show up on the reactant side of the equation. And when that happens, that means that the species is gaining electrons, so we say that reduction is occurring. Now again, don't worry about the fact that I haven't really truly balanced these things. In a true redox reaction, obviously the number of electrons that are required here has to equal out to the number of electrons that are given here. Okay, and I could actually balance these 2 half reactions out to make that happen. And that's ultimately one of the things that we want to learn how to do come class time. But for now, I just want you to see the difference between oxidation and reduction and recognize that I can separate the components of my reaction out into 2 half reactions so I can show those 2 individual events occurring. All right, so we're going to practice more with this in class, and we'll see you then.